Hello everyone, my name is Ashley Goodnight and this is my Lab 1 draft. First, let's move to the introduction. Our problem statement of this lab is as follows. The purpose of this lab is to capture and model the motion of an object moving at constant velocity, then compare the results to a program that predicts the object's motion according to Newton's second law. We care about the conclusions and results of this lab in order to confirm Newton's second law and gain experience with both the tracker and GlowScript programs. In this lab, I was able to successfully model the motion of my object moving at constant velocity under the assumption of no net forces using Newton's second law. As you may have guessed, the main physics principle in this lab is Newton's second law, so let's explain it. The form of Newton's second law applicable to this lab is written here. Final velocity equals initial velocity plus the net force divided by the mass of the object multiplied by the change in time. In this case of constant velocity, aka no change, the net force also equals 0. In this special case, Newton's second law is the same as Newton's first law, which states that when an object has no net interactions with the surroundings, the object moves at constant velocity. For this lab, I collected a sample of an object moving at constant velocity. Let's see it. Here is the video I filmed of my water bottle rolling at a constant velocity that I uploaded to the tracker program. I was able to collect the data on the right after following a couple steps. First, I cut down the clip to only include the middle section to avoid the initial acceleration and to cut out the part where the water bottle hits the wall. Next, I calibrated the measurements using a post-it note. Without a ruler, I used a product of standard size. In this case, a sticky note is a 3x3 inch square. Lastly, I hand-marked the approximate center of mass for almost 200 frames of the video. When we plot the position versus time, here is the graph. Here we see a relatively straight line of the data extracted by tracker. In order to predict the motion of this object, I need to calculate the initial velocity. I started with this equation for initial velocity. My inputs came straight from the tracker program. For initial velocity, I used the first 2 points in order to pop out my answer of 0.364 meters per second. Going back to the equation for Newton's second law, there are a few more assumptions I need to make in order to fully predict the object's motion. In addition to the initial velocity, I am assuming the initial position is the same as the position of t equals 0 on tracker. I selected the ball's radius as 0.0729 meters, which is equivalent to my water bottle's radius of 2.87 inches. Similarly, for my ball's mass, I converted the 11.3 ounces to the SI units of kilograms. I kept both the delta t and the duration the same from tracker. Lastly, I assumed the net force is 0 newtons. I applied these changes to my code. The red arrows point out where I added the main assumptions. My only other change purely for aesthetics was changing the ball's color to black to match my water bottle in line 16. The rest of the code is shown on the next slide. Here's the last of the code, but what's important is its output. Let's see what the program ran. Here we can see the code created a graph visually similar to the observed motion. Under the graph, the code also output coordinates for the position versus time as plotted on the graph. In order to more accurately compare the observational and predicted positions over time, I put them both on the same graph. Now on the same plot, we can see how great the predicted model from GlowScript matches the observed motion from tracker. I do notice 2 areas of small dissonance, which I marked in these purple lines. As one of the EDX videos explained, these periods that don't line up could be caused by a bit of drift back and forth during those time intervals. I would improve my model in a couple of ways. First, the entire duration of my clip was over 3.5 seconds. I could cut this down, say to the time interval from 1 to 2 seconds, where the prediction almost perfectly fits the observed data. I could also account for these sections of imprecision by splitting up my larger time interval and calculating initial velocities for each smaller period. Another adjustment I could make to the code is flipping the axes in tracker. After changing the XY axes by rotating the coordinate system by 90 degrees, here is the new observed data. Looking at the first plot seems a bit crazy until you notice the scale, 10 raised to the power of -3. The first graph is essentially a straight line on x equals 0. It's not until we also plot the y position versus time that the relevant data comes to light. Here we can see that the y versus t graph shows the same data we used originally. In order to complete the lab with these flipped axes, the method is the same with a small adjustment, using the data from the y position instead of the x. Now that we've covered the what if, let's discover the what does it mean. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? Well, let's take this ball as an example. Looking at all of the forces on this ball, it's being pushed and pulled in every direction. But if we slowly peel away the forces that are equal and opposite, we realize the net force is 0. Now, in the case of my water bottle, with only the prior knowledge that the net force is 0, we cannot determine whether it had 1, 2, or all of these forces that were on the ball in this example. With that, I'm concluding my presentation. Thank you everyone for watching!